Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully you guys are doing well. We were in the middle of some examples last time that we're going to finish up. We had 19 examples, I want to say. We did 16 of them, so we'll finish up those 3 and move on to the next topic. At the end of these examples, we would have covered, we covered conceptually everything you needed for your test, like towards the end of last week, but we would have covered all the examples that would be relevant for your test coming up. And we might even start the next section, which, I think we should definitely get to the next section today, which would be given as a bonus on your test. So I think with that said, we can just actually jump into it. So what we were working on yesterday. Let's make sure I can see the chat here. Okay, so I had a bunch of examples. Looked like a lot, but we actually got through a lot. And let's do that. We got through the 16 of them. We learned not only how to do these problems, but just some general principles, best practices that we want to apply, like always applying the simpler rules before the more complicated ones, always looking if you can simplify something before jumping into some sophisticated calculus rule. For example, using your templates as, using your formulas as templates and all that. So yeah, so our test is coming up March 19th, which is Friday, a couple days from now. And just as a reminder, again, there's a review on the class webpage, and there's also a mock test on Gradescope, which I would recommend that you take both of those. So you practice all the material as well as you get used to doing like a test on Gradescope specifically, so you can get used to navigating the system. So yeah, the test I gave when I taught this class last semester, fall 2020, I made that a mock test for you guys. Let's continue. So we had all these examples. We went through a bunch of them. Nothing really to say by way of recap here. So let's actually just go to these guys. All right. So now let's finish these guys up and move on to the next. Where are my notes? Move on to the next section. Okay. All right. This is the notes for the next section. All right, so let's actually do these examples though. Do that first. This guy, tell me how we would go about actually doing that. This one.
Product rule, but you also have to use chain rule.
You also have to use chain rule. All right, so there are 2 things here. There's the F and there's the G. So you know you're going to put F prime times G plus F times G prime, right? And so that is going to be your Y prime. So Y prime equals, what is F prime here?
Uh, 16 parentheses 2x plus 1 to the 7 times x
give
to the
me an intermediate step there. Where did the 16 come from?
The 16 came from putting the 8 in front and then taking the derivative of 2x.
Right, which is 2, right? Yeah, so give me the line like that. Let's not skip the step here. Even though, yeah, you would get 16, but I just wanted you to tell me the intermediate step. So yeah, you do the chain rule. The 8 comes down, multiply, you subtract 1 from the power, but then you have to multiply by the derivative of the inside, so that's where the 2 comes from. So that's why it ends up being 16. And of course, now you multiply by the G. Plus, now we leave the F. All right, what does G prime look like here?
Five x to the third plus 1 to the fourth.
5x to the third plus 1 to the fourth.
And then times 3x squared.
Times 3x squared. Correct. Now, this is the answer. But let's say I wanted you to simplify. As in here, factor, which is going to be useful for the next problem, and something like this might be useful in general, but we'll get to that later on when we start talking about critical points of that and things like that. So yeah, how would you go about doing this? How would you write this as a product, like a compressed form?
Factor out 2x plus 1 to the 7th and x to the third plus 1 to the 4th.
Right. So the first thing you want to do when you want to factor something is you want to identify the common terms. So 2x plus 1 is a common term because it's over here. And x cubed plus 1 is a common term that's over there. Anything else that's common? No, not really, right? So that's it. We're going to pull those guys out. And remember, you always factor out the lowest power. That is the rule. It's always the lowest power every time. Okay, so so we have a 2x plus 1 to the 7th, and we have a 2x plus 1 to the 8th. You always pull out the 2x plus 1 to the 7th. We have the x cubed plus 1 to the 4th, and the 5th, we pull out the 4th. And then you open parentheses or brackets and write what's left over. So what's left over in the first term?
$16.
16. Anything else?
X to the third plus 1.
X cubed plus 1, right? So there were 7 factors of the 2x plus 1. I took out all 7. There were 5 factors of the x cubed plus 1, and I took out 4 of them. So there's 1 factor left, right? You subtract the powers when you pull them out, right? So that's pre-calc. So we know that. Okay. So now we move on to the second thing. What do we have here left over?
$15x squared.
There's the 15x squared. Okay, what else?
2x plus 1.
Anything else? I think that's it, right? So we have that left over. Yeah, so we would clean this up a little bit. So here, notice what I have here. I have 16x cubed plus 16. Here I have, well, 30x cubed plus 15x squared, right? So now I can combine those. So I would have what? Is that 46x cubed plus 15x squared plus 16. Agreed? Is that what you guys got? Anyone there? Okay, so that's that. Now, technically, that doesn't really simplify anything, quote unquote. But as we were mentioning a couple classes ago, there are going to be times when figuring out where the derivative is 0 is going to be important to us. And how would you figure out where this expression up here is 0 is by factoring it and using the zero factor property that you learned in pre-calculus, where you have like a polynomial equation where you have a polynomial or equals 0. How you try to solve that is you factor the polynomial and set each factor equal to 0. So you have to remember how to factor polynomials, factor things of that sort. And the main thing is to find common terms, factor them out, write what's left over on the inside. And there are ways to do this, as well as you need to remember how to like factor quadratics and do factor by grouping and all that good stuff. It's going to come up. So yeah, that's that one. Let's move on to the next example. And I'm also going to want you to simplify this one as we move, go forward. So here, we would use the quotient rule, yeah, because it has division. So we know what that is. So here we're going to use the derivative of f divided by g is f prime g minus fg prime over g squared, where this guy is your f and this guy is your g. So this means y prime. Now these are, you'll notice that it's the same guys from up here. I just, instead of multiplying them, I divided them. Just now I want you to focus on plugging the guys that you already know are the answers into the right formula, not to give you a completely different example. So it's going to be the derivative of the top, which we know by the chain rule, is this times the bottom, x cubed plus 1 to the 5th. Bottom times the top minus the top, times the derivative of the bottom. And this is going to be 5x cubed plus 1 to the 4th times 3x squared. All over the bottom squared. And we know that when we square something to a power, it just doubles the power. So that's the first step. And this is in some sense the answer, but let's simplify. Now you do the same thing. So again, we learned in pre-calculus, you want to simplify a rational expression, you factor the top and bottom and cancel common factors. That's what you want to do. So we need to remember how to factor. And we just kind of reviewed that in a very short manner. So we're going to identify the common terms, which is the 2x plus 1 and the x cubed plus 1. And we're going to factor out the lowest powers. So I'm going to factor out 2x plus 1 to the 7th and the x cubed plus 1 to the 4th. I'm going to be left over with, 16 times x cubed plus 1 minus 15x squared times 2x plus 1. All over x cubed plus 1 to the 10th. In which case this guy is going to cancel into 4 of those, leaving 6. And up here I have 16x cubed plus 16. Over here I have minus 30x cubed minus 15x squared. So now I have the 2x plus 1 to the 7th, and I have 16 minus 15x squared minus 14x cubed all over x cubed plus 1 to the 6th. So like on a multiple choice exam, like I would have written the answer in the last way, the last boxed way. So that's that. Hopefully that's clear. Yeah, so that's that answer. So let's do this last one. What do we do here?
U prime over U.
U prime over U, we have the example, well, we have the rule that the derivative of ln U is U prime over U, okay? So is that what we want to do here? Want to take the derivative of that and then divide by that, knowing that the derivative is this huge monster right here. Remember your training grasshoppers. There is a better way. Think about it and tell me what you think it is.
Could you, oh wait, never mind.
Oh, you're breaking up. I cannot hear you very well. I don't think it's me. Because I can hear James very well, but for some reason you're breaking up, Raluca.
Yeah, because of my AirPods, I think. So
Oh, okay, yeah, I hear you clearly now. Okay, yeah.
Can we separate the logarithm into two?
We can. There's a logarithm, and which means what I was given is also this. And now look at that. Just by applying the log rules, I've now eliminated the need for the quotient rule. Awesome, right? The log rule is a pre-calc rule. It's a lower level rule than jumping into U prime over U. Like me seeing the ln there, I automatically started thinking, well, what do I know about ln's? I can do a bunch of stuff with them. I can use them to manipulate things. I can turn divisions into subtractions. I can turn additions into multiplications. Like I can turn powers into products. Like this is good. So what do we do now?
We put the power down.
You can put the power down. We can actually simplify this even further than it's already simplified. We can take the 8 and move it in front. So now the thing that is inside the ln doesn't even have a power on top of it anymore. Right? Now, of course, we can't really simplify the logs any more than this because we do not have formulas for the log of a sum. But the given problem is actually that. Now, with practice, you should be able to jump from this line and immediately see that. With practice, you should be able to jump here. Okay, all right. So now, how do I find y prime? At this point, you do the U prime over U, right? And at this point, it's trivially easy to do the U prime over U. So the 8 just stays. U prime over U is the derivative of that thing over that thing. The 5 stays. It's the derivative of that thing over that thing. So that's 16 over 2x plus 1 minus 15x squared over x cubed plus 1. Now, you could do the U prime over U thing, but what would you have to do in order to accomplish that? You would have to do this that I did up here, in addition to dividing that by a whole other complicated fraction, right? So someone who just goes into a test and mindlessly just, oh, U prime over U because the ln, you can't, they're gonna, potentially they could still get it right, but look at how much opportunity there is here to get something wrong versus what are the chances you would mess up these calculations, right? Compared to those calculations, right? It's not, right? You're not going to mess this up. You're going to have an easier time. It's left to right out. It's easier for your brain to process. Psychologically, it's an easier way to solve the problem. It's just all good things. And like, let's not even worry about something like this. So using the log rules first, has many benefits. And the situation could even be worse than the above. So like, for example, I could ask you, what is the derivative of ln of like the cube root of, I don't know, x to the 7 times that 2x plus 1 to the 8th over that e to the x times x cubed plus 1 to the 5th, right? Now, if you go into that with the whole, oh, I'm just going to do that u prime over u mentality, technically, you could do u prime over u. And technically, you could even get that right. I wouldn't even say, oh, you're definitely going to get this wrong. I'm not going to be that cynical. But the amount of time and effort it's going to take for you to accomplish u prime over u in this scenario. I mean, think of what look at this guy. What is involved in u prime here? First of all, there's a chain rule because it's inside a cube root function, right? And then you're going to have to multiply by the derivative of the inside. The derivative of an inside is a whole fraction where you're going to have to use the quotient rule. Within the quotient rule, you're going to have to use the product rule because notice that in the numerator and denominator, there are products. Within the product rule, you're also going to have to apply the chain rule because you have that 2x plus 1 to the 8th or the x cubed plus 1 to the 5th. Like, it's going to take you forever. And I mean, so much opportunity to make mistake there. So doing directly by d dx of ln u equals u prime over u is not recommended with a kind of an all caps not red underlined. Right? But by log rules, you would notice that this is the same as the derivative of 1/3 7 ln x plus 8 ln of 2x plus 1 minus x minus 5 ln of x cubed plus 1. And now I can just actually find that derivative pretty easily. So this is going to be 7 over x. This is going to be plus 16 over 2x plus 1 minus 1 minus 15x squared over x cubed plus 1. Right? I can do that in my head almost pretty easily. It's a two-step problem. Now, what I would probably recommend is that you actually try to do this directly as written, only using u prime over u, so that you can actually compare and just know that I'm not just saying this just to say it. Like, there's a reason why I would say apply the easier rules first, right? And it's probably a nice exercise to do it because once you actually sit down and go through it and do it and realize how much torture you put yourself through, you're never going to actually just go into a test and just willy-nilly apply any rule. You're going to know, oh, I remembered when I was practicing, I went through that torture because I didn't just deliberate for a few seconds to think of something nicer to do. And now when you're in the test, you're going to see it. So usually it happens a lot. Like, I would give problems like this on a test, and at the end, students would like complain, like, yo, Jhevon, like, it's a test. You had like 5 problems, and then problem 2, part D was this huge problem that took me forever. Like that wasn't enough time. And it's like, I never expected you to take forever on that. As far as I know, from what I taught you, it's a 2-line problem, and it's not even a hard 2-line problem. What made it hard and what made it take a lot of time and why it was difficult is because you just ran in and applied some rule prematurely, right? And so, yeah, like normally when I'm writing a test and I'm thinking of, well, how much time would be fair for this test? I'm kind of assuming that you guys are doing things the most efficient way, because I actually take a lot of time during class rambling, telling you this is the most efficient way, right? So not everyone does that, but I take the time to write out, hey, you want to do this, this is not recommended, blah, blah, blah. So I'm like, if you listen to me, you'll have an easier time of it. And so I'm going to assume that you're all listening to me. And so, yeah, but just as a reminder to yourself because nothing stings like experience. Like, people can tell you good advice, and yeah, I mean, it sounds like good advice, but you'll just go and do it anyway until you have that experience of, wow, that's what it was like to go through that. I'm never going to do this again, right? So I probably recommend that this was a problem I just made up off the top of my head. I probably actually recommend that you actually go through and do it just directly with U prime over U, compare it to this, and then you're not going to look at logs the same way on a test anymore. You're naturally going to want to do the easier way. And it's not just going to be because I told you. It's going to be because, man, I went through that experience. Never want to do that again. Yeah, but that's essentially it. That's all you really need to know for the test. But let's actually see if we can take a dent out of the bonus material. So moving on to the next section, I want to talk about section 3.5 next. This is where we're going to talk about implicit differentiation. And something called log differentiation. Full name is logarithmic differentiation, but we usually leave out the logarithmic part. We've actually seen both of these guys before, but now we're actually going to look back at them in detail. When I was deriving some of the derivative rules with the chain rule for you guys earlier, I actually used log differentiation and implicit differentiation to derive some of those rules. I used log differentiation to derive the power rule, and I used log differentiation to derive the power rule, which included using implicit differentiation. So yeah, let's actually look at that. Where does the name come from? Well, there are 2 main ways to formulaically define a function. One is called the explicit way, explicitly. This is the way that you guys are all used to. Y equals f of x. There's some formula with just x's in it, and that tells me what the output is, right? So that's an example like y equals x squared, or y equals x plus 1 over x plus 2, or y equals e to the x over ln x plus 5, whatever, right? Y equals something, and on the other side of the something, it's only potentially x's only, but you might not see an x. You might see a number like y equals 5, so a constant function. Versus what we call implicitly. Implicitly means the function is there, but its definition is implied because we don't actually know what it looks like by looking at the formula. So this is like you have some formula that has x's and y's mixed together. So an example would be like x squared plus y squared equals 4, or ln of x plus y minus xy cubed equals 7, or, you know, xy equals 1. These are all implicitly defined functions. The y is not explicitly defined. It's not isolated on one side. You kind of have x's and y's mixed up together. So now here is the thing. We want to be able to find derivatives even in the implicit case. We actually know already how to find derivatives in the explicit case. And how would we actually go about doing that? How would we do this? How do we do it, Captain? The answer, young Padawan, is apply the chain rule. So to find a derivative in the implicit case, this is called implicit differentiation. So it's when you're trying to find y prime. However, you don't actually know what the y is explicitly, because it's kind of mixed up with the x's. How do you actually figure out what the y prime is going to be? Is through implicit differentiation. And implicit differentiation is really just another application of the chain rule. I told you guys the chain rule was like super important. So let's actually illustrate. So let's look at a bunch of things like the following. So if I wanted to find the derivative of, say, some function, okay, versus, say, the derivative of, say, x times some function, versus the derivative. So don't care about what the function is, because you might not always know. So it's just some f of x, versus the derivative of x squared times some function squared, versus the derivative of some function squared, versus the derivative of, say, ln of some function, versus, I have a lot of examples here, versus the derivative of some function all over x. Okay, so let's look at these guys. Now, I don't know what the f of x is, right? And I won't always know. I want to not know what the f of x is. I want you to be able to tell me what is going to be the derivative of these expressions without even knowing what the f of x is, right? And it turns out, formulaically, we can know this. I might not know the specific formulation, but as a formula, I can know this. So what would be the derivative of the f of x? Well, it's just f prime. Whatever f prime is going to look like, I don't know. I don't know what it is. So then there's that, right? But what about this guy in here? Now you have x times some function. You don't know what that function is. Function could be e to the x, could be ln x, could be the square root of x cubed minus 7, could be a constant, could be anything, right? I don't know ahead of time what it is. Can I differentiate this expression? What do you guys think? And what would the derivative even look like?
Use product rule.
You use product rule. There are two functions. So what would you do? You differentiate one, you leave the other one. So you differentiate the x, which is 1, you leave the y, plus now you leave the x, you differentiate the y. That expression would be the derivative. Okay, moving on to this one. What would we do now?
The same thing.
Product rule? So what would that look like if I take me through the motions here?
So 2x times f squared
Yeah,
plus x squared times 2 times f of x.
that's it.
And f of x times f of x.
Come again? Times what?
Should it, like, at the end, should you write like times f of x prime?
You need f prime of x multiplied by x prime of x, right?
Yeah.
And y is because you had just applied the chain rule. Now we've been doing it the whole time, but you just wouldn't notice it here because applying the chain rule in this case becomes multiplying by like a 1. But here you can actually see it explicitly. Ironically, we're doing implicit differentiation, but you can here see explicitly the chain rule being applied. My f of x, I don't know what it is. It's some function, but it's all squared, which means I have to think of the square as an outer function and my f of x as an inner function, which means I have to differentiate the outer function, then multiply by the derivative of the inner function, right? So I'm going to multiply by an f prime, right? What I just did, let me isolate that example, is just the derivative of this is you differentiate the outer function and multiply by the derivative of the inner function. Okay. Okay, so that's what that derivative expression would look like. What about the ln? How would I differentiate ln of the f of x? What would it look like?
F prime of x over f of x.
Right. U prime over u, chain rule. So again, chain rule. What would this one look like? F of x divided by x.
Bring the x to the top and do product rule.
Yeah, that could work. Let's leave it as quotient rule for now, though. Because we already have examples of us doing product rules. So I actually want you to think about this within the context of the quotient rule specifically, because you might want to do that later on. So I would apply the quotient rule here. And how would it actually look to write down the needed expressions?
Is it f prime of x times x minus f
Yeah.
of x over x squared
Minus f of x
over x?
over x squared. Right. So and that's by quotient rule with chain rule. Okay. So we somewhat have the idea. Now what I want us to do is I want to compare this to I'm just going to do a slight change in notation. That's all I'm doing. Like nothing is going to really be different. However, instead now, instead of writing f of x, I'm going to write y as f of x. So compared to, here what I want to do is replacing f of x with y, because that's how things are going to appear later on. So I know if I want to differentiate y, what is the answer? Well, just as above, it was y prime. If I wanted to differentiate, what do I have? xy, right? So instead of x times f of x, it's just I'm differentiating xy with respect to x, right? What would that look like? Well, it would look like exactly like what we figured out before, except now instead of f, you write y. So this would look like y plus x times y prime, right? If I wanted to differentiate x squared times y squared, what would that look like? 2x times y squared plus x squared times 2y y prime, right? Why? Because of the chain rule, like we did it above. If I wanted to differentiate an expression like y squared, like what we have above, well, that is just going to be 2y y prime. What if I wanted to differentiate an expression like ln of y? Well, that would be y prime over y. What if I wanted to differentiate an expression like y divided by x? Well, that would be xy prime minus y all over x squared. That's what the derivative would look like, right? So we can actually compare these two. And I don't know if I want to make these line up a little more than I made them line up. I don't think it's terribly necessary. I think you guys can see what I'm doing here. Okay, so you have all these expressions. And this is how we're going to be like differentiating stuff. That has some unknown function involved, right? And we want to be able to get to expressions, right? So now there are a couple things that intuitively I want you to get at that might not, yes, knowing that, oh, I'm supposed to apply the chain rule, it's not, from a learning perspective and really understanding how to do things, it's probably not going to be enough for you to do that, or you don't want to, it's not very helpful mentally. So I do want to give you some intuition behind this. When differentiating implicitly, some expression. One, you want to identify the independent variable. Independent. This is often going to be obvious. It's usually, if the x's and y's show up, it's usually going to be the x, and we kind of are used to that. but I will, and it does show up that we have other variable expressions showing up from the time to time. Identify the independent variable. So in dy dx, we know that the x is the independent variable. Okay, so you need to know who that guy is. I know whenever I see an x, that's an independent variable. If I see any other symbol, it's not the independent variable. It's some other function, right? So just knowing who is the independent variable is going to be very important. Secondly, what you're going to do is you would differentiate the expression as usual, applying all applicable, oh God, all applicable derivative rules, but with one difference. Whenever you differentiate a variable that is not the independent variable, you must multiply by the prime of that variable. Why? Chain rule. Because that variable is going to be considered a function of the independent variable. So it's like an outside function that you have to keep multiplying by the derivative of the inside, right? That's how you want to think about it. So essentially, when you're differentiating expressions, you go through and you differentiate as usual in the sense that the product rule is still a thing, quotient rule is still a thing, chain rule is still a thing, everything is still a thing, except when I go through and I differentiate an x, I just differentiate the x according to the formula. If I differentiate a y, though, I need to multiply by y prime. So for example, here, notice in this term here, I differentiated the y squared. Differentiating a y squared means applying the power rule. But because the y is not an x, I had to multiply by the prime. I had to multiply by a y prime. So because I was differentiating a y, I had to multiply by y prime. When I differentiated an x, I didn't have to multiply by anything. I didn't multiply by an x prime. Though technically I did, but the x prime is 1. When I multiply by something that's not an x, when I differentiate something that's not an x, I have to multiply by its prime, just automatically. So I go through, whenever I differentiate something that's the independent variable, I don't do anything special. Whenever I differentiate something that's not the independent variable, I multiply by the prime. So that's the intuition. Differentiate anything that's not an x, multiply by its prime. If you differentiate by the x, if you differentiate an x, you don't really do anything different. Third, you may isolate the y prime if you need to solve for it. So there are a couple examples that I wanted to slowly inch our way into, but I think what I will do now is give you one of the general, more quick examples, just so that you have a chance of actually getting this as a bonus on the test in the way that it would be presented. So, so I'm going to give you one of my later examples, and then we'll go through some examples where I kind of build up some motivation for some more motivation. Here's an illustrative example. Okay. Suppose we have 4x squared plus 2xy minus 3x squared y squared plus 4 equals 7 minus ln x. And I ask you to find y prime equals dy dx. Okay? So here is an implicitly defined function. The y is not isolated. However, I care about finding its derivative anyway. This requires implicit differentiation. Intuitively, all this means is you just go through and you differentiate as you normally would. The only difference is whenever you differentiate a y term, you multiply by y prime. So this requires implicit differentiation. So you would go through, differentiate as usual. However, when differentiating a y term, multiply by y prime. In the end, you must solve for y prime to obtain the desired answer. Okay, so let me quickly go through and actually do this one for you guys, and then I'll let you go. And of course, I won't see you next class because you will be doing the test, but then class after that, we'll pick up with some more examples on implicit differentiation. Okay, so you'll have this, and the goal is to find y prime. What do? Well, you go through, differentiate as usual, derivative of 4x squared, 8x, plus derivative of 2xy. Oh, there's an x and a y. For this, I would need product rule because it's the product of functions. What does the product rule say, right? Differentiate one function, leave the other, plus differentiate the second function, leave the first. So if I think of these two functions as, you know, like 2x and y, product rule says differentiate the 2x, leave the y, plus leave the 2x, differentiate the y. Derivative of y is 1, but because I differentiate a y term, I multiply by y prime. Chain rule. Minus, now I go in and I do this again. Again, there's a product here. There's the 3x squared and the y squared. So again, I'm going to use a product rule here. So then I'm going to differentiate the 3x squared, that gets minus 6x, leave the y squared, minus, because I would distribute the minus sign across the plus, leave the 3x squared, and differentiate the y squared. Now I want to differentiate a y term, hence I'm going to differentiate as usual with the power rule, and then multiply by a y prime, because it's not the independent variable. Derivative of 4 is still 0 because it's a constant, so I move on to the next side. Derivative of 7 is 0 because it's a constant. Derivative of the ln x is 1 over x. So I have now gone through and I differentiated each term. And I do this as usual, still applied product rule whenever it was relevant, still applied all the rules whenever they're relevant. The only difference is every time I applied a derivative rule to a y term, I multiply by a y prime, right? So every time I'm differentiating a y, multiply by y prime. So then I get this. But now we need to isolate the y prime. Because that was what we were asked to do. So here you'll notice that there's a y prime here, there's a y prime here. I want to isolate those guys. So now you're going to solve it just like an equation. From here on, it's just algebra now. All the calculus is done. From here on out, it's just algebra. I want to isolate this thing in an equation, which means I want to leave all the things with that thing in it on one side of the equation, and then bring everyone else to the other side of the equation, right? So that's what I'm going to do. So here, I want to leave my 2xy prime minus my 6x squared y prime, right? So I've just isolated both of these y primes here. And now I'm going to bring everyone else to the other side. So I'm going to move over the 6xy squared. I am going to move over the 8x. I am going to move over the 2y. I am going to move over, oh, that's it. That's all the other guys. And then there was already the -1 over x hanging out over there. Now to, of course, continue, we know that we factor the common term out. And now I can solve for y prime. So here, factor out common y prime. And so now I can just divide both sides by the expression multiplying the y prime. So I get 6x y squared, 8x minus 2y minus 1 over x, all over 2x minus 6x squared y. And that would be the answer. Could simplify here by multiplying by x over x. Which is probably how the answer would be written in a multiple choice option if I gave you that. So that would look like 6x squared y squared minus 8x squared minus 2xy minus 1 all over 2x squared minus 6x cubed y. Just so that you don't have a fraction inside of a fraction, like having this, the 1 over x here, kind of unaesthetic. So that would be the answer. Now, yes, you might notice that within the derivative answer, there's a y there, which is, it's not strange for implicit differentiation. I'll explain to you how we can deal with that, what it means, what problems can arise from this or not in the next one. But that's it. You now have enough material for the test and even the bonus problem. And I'll probably throw in some more bonus problems from linear approximation, I think, and something else. I think the mock test actually has some of the types of bonus problems I would even throw in after that. So, but for now, that's what we're going to do. So that was implicit differentiation. Technically not on your test, but if you want to get some extra points, you might want to know how to do that. So yeah, we will stop there. Hopefully that was good. Thank you for your time and attention. And I'll let you guys go now.
Professor, I have one question.
Yes.
The test will be entirely on Gradescope. It'll be
Yes.
only on Gradescope.
Entirely on Gradescope. So for class on Friday, you're just going to log into Gradescope directly. And you'll see it there. You'll see test 1 pop up. You click on it. The instructions on the test are going to be the same as on the mock test. So if you know the instructions, you don't have to waste time reading them again. But yeah, that's it.
And it just runs from class time, right? And
yeah, just runs
okay.
during class time. So the test is going to run during class time. You will have an extra 15 minutes or so beyond class time for uploading, but technically you don't need it. But yeah. All right, so that is it. All right, good luck studying, and